Lexical and syntactic analysis are the first two phases of a programming language translator. There are two with which we work most frequently: interpreters and compilers. We will see how we implement a lexical analyzer, or scanner, and the syntactic analyzer, or parser. A translator for a programming language allows us to take the version of a program that the programmer wrote, the source code, and transform it into a version that the computer can make sense of, the object code or the executable code. There is a significant difference between the object code and executable code, and we will talk about this shortly. Compilers translate programs that are written in higher level languages, such as Fortran, C, or C++. For this reason, the translation process takes more time than that of an assembler, but it allows the programmer to work in a language in which they are much more comfortable. Compilers, unlike interpreters, save the low-level version of the program that they create. This low-level version is typically in machine language and usually for the computer on which the compiler runs, although there are exceptions. Most compilers create object code, a translation of the program into machine language, but it is not ready in that form to run on the computer. The operating system will usually require that the executable version of the program have a particular format. This format will vary from one operating system to another, and it has to have the complete program, including any library procedures that the source code may make use of. And the source code may consist of several different files containing different components of the program, some of which may be used in more than one program. When a source code file is translated, there are references made to both variables and procedures that can't be resolved because they are defined in other files. These unresolved references are resolved by the linker, which also creates a version of the program that includes not only the resolution of these references, but includes a copy of all the procedures that the program uses, including object code from various libraries, if they are used. A good analogy for the unresolved references is the front page of the New York Times, where most articles continue inside the newspaper. Since they do not know where the articles will continue inside when the front page is composed, it will read continued on page blank until they compose the inside pages, and then they can replace the blank with a page number. While compilers may have an option that allows the programmer to choose to create an assembly language version, this is not always the case, nor is it a necessary step. The option exists so that the programmer can see what a low-level language version of their program will look like. An interpreter is different from a compiler. While it may do some preliminary processing to create an intermediate representation, it simply translates the program one statement at a time, executing it, and moving on to the next statement, without saving a translated version of the program. While this allows the program to start running more quickly than if you had compiled it at first, the compiled version of the program will lead to faster execution speeds. A compiler is organized into a front end, which handles the more language-dependent phases of the compiler, and a back end of the compiler that handles the more machine-dependent phases of compiling. There is usually an intermediate representation of the program created by the front end and used by the back end. This allows a front end for a given language to be matched with the back end for a given machine. The front end of a compiler is centered around the syntactic analyzer, or parser. It has the job of determining the grammatical structure of the program. When it needs additional tokens from the lexical analyzer, or scanner, it will call the scanner, which will return a token to the parser. When it needs to have a particular semantic action performed, it will call that action. It is important to keep in mind that semantic analysis is not performed by one monolithic module of the compiler, but by separate semantic actions that get called when the parser determines that it is necessary. And lastly, as it is necessary, the parser will have the intermediate code generator create all or parts of the intermediate representation. Lexical analysis, or scanning, takes the stream of characters that are inputted and groups them in a meaningful way. The result of the process is that we get a token, which is a representation of some aspect of the language's grammar. The scanner goes through the input one character at a time until it finds a character that does not belong in the lexeme. It then looks up the lexeme in the symbol table and returns the token to the parser. It will usually also supply a reference to its symbol table entry, so we can use its token and have access to other information about the lexeme, including its data type. The parser's job is to examine the syntax of a program and determine whether or not it adheres to the programming language's grammar. Although the parser will go through many of the motions of creating a parse tree, it actually does not create one. We will embed in the grammar the semantic actions that we want to implement, and one of the things that it will do is generate an intermediate representation of the program. As we have already seen, semantic analysis is not one module, but a collection of different procedures that ensure that the semantics, or the meaning, of the program is correct. In most cases, the aspect of the semantics that we are most interested in is type checking, making sure that data items are used in a way that adheres to the requirements of the data type. While syntax and semantics are related, they are by no means synonymous. It is entirely possible for a program to be syntactically correct while it is semantically incorrect. The semantic actions are implemented as separate procedures that are called when the parser encounters an action within one of the productions that comprise the grammar of a programming language. And again, they are not a separate phase of the compiler. One of the most common intermediate representations is the abstract syntax tree, since we can annotate it, and this information will be very useful when we are ready to generate object code. The one component of a compiler that interacts with all the phases of a compiler is the symbol table, which stores all the data about each lexeme appearing in the program, including its reserved words, literals, standard and programmer-defined identifiers, which include programmer-defined variables, data types, and procedures. The data that the symbol table stores concerning the lexemes includes the lexemes themselves, their corresponding tokens, the scope of the program in which the identifier is known, and their data types.